So if you take an element from that set, it'll be of this form. Right? So this, these square brackets and a suffix down here. So that is the residue class mod n. So this residue class are all those integers, by definition, all those integers that are congruent to this integer r mod n. Right? That's what a residue class is, right, by definition. Okay, so we're going to map one of the residue classes of this group, or set, if you like, into some member belonging to this cyclic group. Right? And this cyclic group has order, group order, okay, group order, and little n. Okay? Group order. Okay. All right, that's our that's our proposition. That's what we propose for the mapper F to be. All right. Now, is it well defined? So let's now remember from earlier discussion. This integer here is a representative. It's just one possible integer you could put here. I mean, you could, instead of r, you could put r plus n, or r plus 2n, or r minus n, or r minus 2n, dot dot dot. There's many representatives of your residue class you could put here. So a bit of discussion on is it well formed. So say you had a different representative. Say you had S here. So say you tried this. You put an S here. And such that these two, so that R and S are congruent, mod n. Does it make sense if I do that? Would I get an S here? Does that make sense? So, question mark. Will I get an S here? I mean, if I don't, I'm in problems, right? Because R and S here, they're congruent, and therefore this residue class R mod n is the same thing as residue class of S mod n, because R and S are congruent. This set here includes S, right? And this set here includes R, so they're the same residue class. So if I don't get A to the S, if F of this residue class does not map to A to the S, I've got problems, right? So I need to prove that mapping this residue class with representative S, I get this, right? So in other words, I need to show that A to the S equals A to the R, right? Because these are the same in terms of residue class. So how to prove that? All right. Well, if these two are the same, if residue class R mod n is equal to residue class S mod n, that implies that R is congruent to S, right? Mod n. And what can I conclude from that? Well, now we can use the second part of theorem 18. Right? That's why we talked about it. And the second part of theorem 18, talked about some minutes back. You can remember what the conclusion was? So if this is true, if R is congruent to S mod n, So from theorem 18, the second part, what do you know? You know that a to the r equals a to the s, right? Where a is your generator, finite generator. Okay, so that result just came from theorem 18, part 2. Okay, so it's well defined, right? So we've shown that. So if R and S are congruent, then f of either residue class R or S mod n both give you a to the R. Right? So if it's a to the S, it equals a to the R. So we proved that. So it's well defined. Okay, so that's the first part. All right, now we have to prove bijection, and that means we have to prove injection and surjection. How to prove that? So I guess in a similar way, right? Here, concentrate on this. Now here, I'll just draw a diagram similar to this. Okay. Now what are we doing? We're now mapping a residue class. Well, little r here. A residue class into what? The generator to power r. Okay. Now we're going to prove surjection first. Very similar reasoning approach as to this problem. Yeah, to part 1. Now for any member in your codomain, it's a member of this. This is your cyclic group of order n, the group of order n. Okay. So any element will be of this form. It'll be the generator to some power r. But from this, you know that for every r, integer r, and by the way, this r here will be less than n and greater or equal to 0. Why? Because it's a cyclic group. So the generator, now can you remember that in a cyclic group, the order of the generator, in other words, the order of a particular element, is equal to the order of the group, right? Because that generator generates or creates the whole group, right? So the order of the element, the generator, G, little g, if you like, its element order is equal to the group order. So this R here cannot be equal to n, right? So if this is n, by definition it'd be E. Well, that takes you back to here. And here we get this cycling again. That's why it's called a cyclic group. Okay. Right. So for any R here, you'll have a residue class R here. So every element here is mapped to, because for whatever R you have here, you'll have the corresponding R here, and this R lies within this range. And this set here, what is it? Well, it's z to the n, right? And it will have n residue classes in it, ranging from 0 to n minus 1. But that's what R ranges over. So you've got this nice one-to-one mapping. Every point in this codomain gets mapped to by the corresponding residue class. Okay, so surjection. Okay, right. Every element is mapped to, so the mapping is surjective. Injective. Well, again, just take two of them. So take two of them. So f of A, f of B. The usual injective type proof. Assume they're the same. So just assume that FA is FB, and we have to show that A equals B. Right? Oh! No. Here's... actually, that's a good little bit of education. I was going to do it from first principles, right? But you know, by proving that A equals B. Now, you could do it that way. But the course, we already have a whole slew of theorems we've already proved, right? So why not use them? You know, we can use a previous result if it can speed things up. So here's a more elegant way to prove injection. Now we're mapping between two groups or two sets, right? Now they have the same size, and you're probably going, okay. So we're going to use theorem whatever it was. These two have the same size, right? The two groups have the same order. And why is that? Well,